nice manner. For this purpose, we have to depend upon data encryption standard. How we are going to using it, we have to ensure that DS construction, the DES or data encryption standard is designed by researchers at IBM in early 1970s and adopted by the US government in 1977. This is the first encryption algorithm for the commercial and sensitive data is being maintained in the databases, and a lot of information is being communicated, and how we can maintain secrecy about it. To do that purpose, the encryption algorithm is being used. Data encryption and is the first algorithm is being introduced. It is used in top and we make data encryption to 64 means when the plain text is given to us, the plain text has been split into many 64-bit blocks. The first plain text box P1, second P2, P3, like that we are going to combine. The P1 plus P2 up to Pn combined together, it is representing the plain text. So as soon as we get the plain text which is in the form of text must be converted into digital form. It has to be split into 64-bit blocks. We get many such blocks after splitting original plain text. Now in this is the block size message. For encryption, two important aspects are required. One is the message, which is we are having as a P1 plus P2 plus P3, like that, combination of many 64-bit blocks. And then we require the key. Both shall be supplied as input to encryption algorithm. So in DES, the key size is 56 bits. Please remember, the block size of 64 bits and is related to the plain text. There is another input, separate input, which is a key. Its size of the key is 56 bits. Actually, 64 bits will be there, but 8 are used as parity check bits for error control. And we know in the communication networks, that is how we are going to create, how we are going to add on the check bits for parity check bit and other things to that. So like this, out of 64-bit key size, 56-bit is representing the key, and remaining 8 bits are being used for parity check, so that we can have a good error control. And when we want to convert original plain text into the ciphertext, we are making use of 16 intermediary keys and rounds. There will be total 16 rounds. For each of the round, we will be having the input plain text, which is there will be some transformation, round 2 to round 3, another set transformation. Like that, message is in a stepwise manner. In 16 rounds, we are converting the plain text in the final text. In each of these rounds are coming as for each of the rounds. In brief, 64 bit plain text of parity check bits. So like this, block 1, then block 2, block 3, block 4 of the plain text are being converted. Key 64-bit, this is what we can see here. We supplied, then a DS cipher, 64 cipher text. So to do that thing, we require the 64-bit key. This is happening at encryption side. And this 54-bit key between the sender and receiver in cryptography, the key should be known to both of them. It should be shared. Since the receiver end, the person is knowing the key, the ciphertext is being supplied, and this 54-bit key, then from the last text which we are getting after 16 round, in the step by step from bottom up manner, 16 round to 15 round, 15 round to 16, the 14 round, like that, in a bottom up manner, we move and then we'll get original plain text. Here, top down, round 1, round 2, round 3, up to round 16, we convert original plain text by splitting it into many blocks. For each block, using the key and intermediate keys in each of the rounds, we convert the plain text into ciphertext. At the receiver side, the ciphertext, we start reconstructing plain text. So we move from what is the output of the last round to output of the 15th round, then 14th round, like that. We move up and then we get the original message. That is happening at the encryption side. For that purpose, we are having an algorithm. Look at it here in the picture. For different types of keys, different type of ciphertext we are going to get, though plain text is same. So how we are going to do it? The original, the block that is from plain text, we split. We pick up block 1, which is having 64 bits. And making use of initial permutation, this 64-bit has been split into left side we are having 32, right side we are having total 32, which combined together is 64. Now after that, we start converting into right one, where the left part is being not at all. The encryption of the right part of the 32 bit that we are going to carry out. For that purpose, we are having algorithm. Then we have got a sub key, and this combination is performing S box substitution. And once substitution is being carried out, then we perform permutation. What is substitution and what is permutation? Already we have seen. These are the two types of the ciphers. In the two types of ciphers, we have to carry out substitution, then we have to go for permutation. Because of this, we are going to get the ciphertext out, which is again 32. We combine it with this. The left side in the next round. And this, whatever we are getting as the output, the left side of it is becoming the right side. Then we carry out, in the output we have got 64 bits. The first 12 bits are unchanged, and the 32 bit new one is being changed, has undergone change. Now in the next round, that is in the third round, right side of this 64 bit is becoming left part of the input, and left side is becoming the right side of it. Means when we move from round to round, what we do, we keep left fixed, we make the changes to the right 32 bit, and in the next round what output we get, we keep 32 as fixed. The earlier left side of the message, it undergoes change. Then in the next round, what output we are getting as 64 bit, out of that 32 right side will be becoming a left side input, and left side is becoming the right side. Like that, we move from one step to another step. Each of several possible ways of permutation are being round of 6. Then this permutation become more and more complex. Overall objective is making use of the keys, performing encryption by having providing greater security. Now in data encryption standard security, it is the old data encryption standard. Its key size already we have seen, it is 56 bits, and also DS uses 64 bit blocks, which raises some potential issues. Encrypting several gigabits of data with the same key is being carried out. But however, when in the earlier things, when we are having a lot of problems related to CPU speed, and also when there were constraint on us from the database angle, and when there were constraints related to the speed of the computer networks and other things, we had to deal with the size of the data. But in modern days, because of the evolution and revolution of communication related aspects and database related aspects like big data and other things, and these things are not playing a greater role, means a size of in the form of gigabyte and other things. In modern days, it's a very small entity. Now, when we provide all these things, so the brute force attack on DES is being used to recover the information, because we may be using either the confusion or diffusion here. Because of that, either the relationship between the key and the plain text may not be clear, or the relationship between plain text and the final, the ciphertext may not be clear. If any of these relations are missing, then what happens is there will be always confusion or diffusion between the sender and receiver. If receiver wants to recover, then he has to use the brute force attack on DES. It involves search of the key space. What is the possible key? Like that we have to search. That is testing all possible keys in order to recover the text used to produce a ciphertext becomes very crucial. The expected number of trials before the correct key is found is equal to half of the size of the key space. So much search we have to do it. For example, if there are 264 possible keys, a brute force attack would on an average be expected to find a key after 263 trials in the worst scenario. So like that, the different type of searches we have to do in the key space to get the first one. It is as if to open any Almirah, we have got one box in front of with thousands of keys. Then how we are going to pick up the right key to open the Almirah? We pick up one, we try it. If it doesn't work, we pick up another one, we try it. If it doesn't work, we go to the third one and try it. Like that, we go on checking. The similar type of thing is happening here. If the key is not known, then what happens is, what are the possible combination of the key? We should go on searching and searching and searching till we'll get. In the worst scenario, there can be in 264 possible keys, then 263 maybe take place. Now, with this, we shall move towards block cipher. But is a design model. Please remember, it's not a standard. It is one of the models. There can be many different models, but this is a very popular one. Is a design model from which many different block ciphers are derived. DES is just one example of a Feistel cipher. A cryptographic system based on Feistel cipher structures uses the same algorithm for book and decryption. Only difference is in encryption top down, in decryption bottom up. We have to use the algorithm in a reverse manner. Already we have seen the DES block size of the text is 64 bits. Key is either 56 or 128 bits. For our thing, we have taken 56. A single block of plain text is transferred into ciphertext after passing through the following steps. An initial permutation, 16 rounds of a given function, a 32-bit left-right swap, 64-bit input, we are splitting into 32-bit left and right. Already we discussed on that, and a final permutation. How it is taking place? Each of the 16 rounds are functionally identical. If we understand that what is happening in the first, then in the next block what happens? in third, what happens like that, we can conceptualize or imagine. Let I minus 1 and R I minus 1 be the left and right side of the input to round I. Means from the earlier round, what we are getting, they are becoming the input to the next round. So LI1 means and LRI1 32 bit and 32 bit output of earlier round is becoming input to the next round. So since we are considering round I, Li minus 1, Ri minus 1, which are obtained from earlier round, are coming as input here. Li equal to R minus 1 means we keep left side fixed. Whatever has been supplied to as the right side of earlier round becomes the input Li here, left part of 32 bits. And what was the left side of the output of earlier round is becoming the right side here. Then we are carrying out the XOR function of Rj minus 1 and Kj. This is what we are going to carry out. The function f is applied at each round and is referred to as the round function. Each round uses a round key, which is one of the inputs to function f. Each round key is derived from the ds key. Some formula we have to use, and using it we have to derive from the ds key. The encryption process using the Fechter structure consists of multiple rounds of processing of each plain text. Each round consisting of a substitution step followed by a permutation step. We had seen in earlier diagram. So original message from earlier round output is split. Right side becomes left side of the message which is being supplied as input to the current round. Left side of earlier output becomes right side of it. So left part we do not change it. Right part is undergoing change. First we perform substitution. Then after that we perform permutation. For that purpose, key is being used. The round key is being used there, which has been derived from ds key. Then the transformation takes place. After carrying out the first substitution, then permutation, then we will get the output. Output again is a 64 bit, and we split the 64 bit into 32 bit, 32 bit. Then left side 32 bit is becoming right side, and right side 32 bit of output is becoming left side of the input to the next round. Like that, we carry out 16 rounds. This is the schematic diagram how the activity is being carried out. Now the plain text has been supplied, so there is a bigger message. Now we are taking one block from that plain text. So it has got two halves. One is L and R, 32 bit and 32 bit. So that is being supplied here. Then right side, for this we are supplying performing function applying the function, which is combination of key and right side message. And how this particular function is getting carried out. This is the way it is carried out. Means left part is the same, but right part is undergoing change by considering a round key as the input and by making use of substitution, following that permutation. These are the activities we carry out. then we'll get the output. Output is actually 32 bit of the right part that underwent change and left part which has not undergone any change. Now in the next round, the right part of it is becoming left side and left part of it becoming right side, so that it can undergo change. Like that, round 1, round 2, round 3, like that, up to 16 rounds of activities we carry out here. So left right swap becomes very crucial of these 64-bit combinations. Finally, we get the ciphertext. Whatever we are getting after 16 rounds is actually encrypted. So the algorithm design decides on number of rounds. Each round involves substitution and permutation steps. The input block to each round is divided into two halves denoted as left half L and right half R. Round R goes through unchanged, but L goes through an operation that depends on R and the encryption key. First, apply an encryption function F that takes two input, the key K and R, right side of the message. Then it produces the output after applying the function. This function is a combination of substitution first, after that permutation. Then XOR the output of the FKR function with L is obtained. In DS implementation of the Feistel cipher, in each round, instead of the whole encryption, a round dependent key, which is called as a sub key or round key, is derived from encryption key. Each round uses a different sub key related to the original key. How we are going to arrive at a uniqueness of the Feistel encryption, the algorithm. The permutation step at the end of each round swap the modified L and unmodified R. L for the next round would be R of the current round, and R for the next round is actually the output L of the current. Once the last round is completed, then the two sub blocks R and L are concatenated in this order to form ciphertext block. Now we shall see how the decryption process is going to take place. In the decryption process involves Li minus 1 and Ri minus 1. We are moving the bottom up here. Means what is the final ciphertext? From there, what will be in the round number 15? From round number 15 to round number 14, like that. To carry out that, we use bottom-up approach and is summarized by the following equations. Ri minus 1 equal to Li, Ri minus 1, Li minus 1 equal to Ri plus the function of Li and Ki. Note that decryption 2 involves computing the function, not the inverse of a function. The implication of this fact is that the function f does not even have to be inevitable. The structure of such a cipher is attributed to Horst Feistel, one of the key designers of DES. A cipher that has such a structure is referred to as a Feistel cipher. The process of decryption in Feistel cipher is almost similar and not exactly same. Instead of starting with block of plain text, the ciphertext block is fed into the start of the Feistel structure, and then the process thereafter is exactly the same as described in the given illustration. Means only the output of the encryption is being used as input for decryption, and everything is the same. So with this, we come to the end of the session. In today's session, we have discussed about secret key or symmetric the key cryptology, and we have discussed about confusion and diffusion, and we discussed about the block structure and its use, and we discuss on DES, then finally Feistel encryption process and decryption process. So that is the overall scope of today's discussion. With this, we come to the end of the session. Thank you.